Okay, conservative forces, potential energy. That's what we want to talk about next. And the way that we'll do this is by just looking at a system. It's pretty straightforward, hopefully, and simple. We take just a box, and we're going to move the box from one location to another location. And we're going to calculate, this is the same box, they don't look the same. You know what I could do actually? Could actually just copy the box, right? So I could take this box, let me just copy paste it, move it right up here. Okay, so there's our box. It moves from this location at the bottom to the top. We're going to say that it starts off with a y coordinate. We'll say that the initial y coordinate right here, and we'll draw that y coordinate up to the center of the box. We'll call that y sub 1. Okay. And I think we want to make positive y direction up, if I remember correctly. Positive y will go up. And then we'll move the box to another coordinate that we'll call y2. All right, so that it moves along a displacement, from, we'll use blue. It moves along a displacement that goes in that direction right there. Okay, that would be its displacement vector. And the value of this should be, I think, something like delta y, and it's going to be equal to like y2 minus y1, right? The box moves up, okay? Okay, so someone's pulling the box from here upwards, and this object is obviously subject to the force of gravity, and so we'll label on here what the force of gravity is. The force of gravity would point this way. Let's just call it mg. And again, here it's going to also be mg. The force of gravity will be about the same over almost any elevation that we choose here. And we can say that the work done, oops, it's kind of ugly. We can say the work done by the force of gravity should be equal to, the force, which is mg, multiplied by the distance the object moves. I don't know, I didn't need to erase this. This is y1. So we have to multiply by delta y, or in this case, y2 minus y1. And we'd also have to multiply by the cosine of 180 degrees. Because the vector for delta y is up, and the vector for the weight is down. And so as a result, we get this cosine 180 sign that shows up here. So ultimately, we get this. This is equal to negative mg multiplied by y2 minus y1. Okay? So now we got to think about something just in general about the way that work and forces interact with each other. When you lift an object up, right, gravity naturally wants to allow that object to return back to where you lifted it from, right? So you take a ball and you lift it off the ground, you let go of the ball, it falls to the ground, right? And our goal here is to describe what happens when you lift an object. In what way can we think that the object has gained energy, right? Well, when you do work against gravity, gravity is always going to be able to basically give that work back to you in the form of energy, okay? You lift an object up, it naturally will fall down, right? You get on your bike on a hill, and you'll naturally roll down the hill, right? You don't need to do anything to make that happen, right? It's just the way gravity works. It makes things move downwards. So when you lift an object up, in some sense, we can say that you've given it something. You've given it some kind of an energy, okay? And that's what we call potential energy. And so I'm gonna write an equation down right here and say that we want to define the work done by gravity, and we want to say that it should be equal to some kind of change in a quantity that we're going to call potential energy. Okay, but the thing is that when you lift something upwards, the work done by gravity is negative, right? Like if y2 is greater than y1, right? The work done by gravity is negative. Whoops. And if y2 happens to be less than y1, then that leads to the work done by gravity being greater than 0, right? And this is lifting. and this would just be falling or lowering. Sorry, bracket this off. When you lift an object, the work done by gravity is negative. When you let something fall, the work done by gravity is positive, right? So that means that if I want to describe the energy that's gained when I lift an object, the work done by gravity is negative. So what I need to do is I need to put an overall negative sign in here and say that the work done by gravity is going to be the negative of the change in potential energy. We're going to use the symbol U for potential energy in this class. So this is going to be our symbol for potential energy. And we're going to say that the work done by gravity should be equal to the negative of whatever the potential energy is at point 2 minus the potential energy at point 1. And we're going to connect that to this expression up here, the mg y2 minus y1 thing here, okay? We see a negative sign show up on both sides, which means that basically u2 is equal to mg times y2, and u1, the potential energy at point 1, is going to be mg times y1. And in general, we define potential energy to just be mass times gravity multiplied by the position. And this is just the potential energy due to gravity in particular, okay? mg, you may have learned in your last physics class that the potential energy due to gravity is mgh. In this class, we just say mgy, because it's the y coordinate of the object that determines what the potential energy due to gravity is, okay? This relationship right here is a general relationship, okay? So I'm going to stop for a second and just make sure you guys understand everything here. But the general relationship that comes out of this expression here is that if I have a conservative force, if I have a conservative force, the work done by a conservative force is always, there's always a potential energy, okay? The work done by a conservative force is always equal to the negative of the change in the potential energy for that force. This is a relationship that is completely general. I think it's something that you derive in calculus, and we just did it for gravity, okay? And we'll do it again for springs. But the work done by a conservative force is always equal to the negative of the change in potential energy. When I lift an object upwards, it gains energy, right? You lift an object up, the y-coordinate increases. So this would be, up here we could say this is high potential energy, and this would be low potential energy by comparison, right? So when you lift an object up, you give it energy, right? You give it this type of, potential energy stands for a type of stored energy. You store energy in the field of the earth, right? When you take a bow and arrow, for example, and you notch a arrow into the bowstring and you pull the bowstring backwards, it's also a type of stored energy. If you compress a spring, you can store energy. If you stretch a spring, you can store energy. So potential energy in general is a type of stored energy, right? And, yeah. Do you guys have any questions? This relationship is pretty important to understand. It shows up in a lot of physics. It shows up in 1A, 1B, 1C, 1D. That the work done by a conservative force is equal to the negative of the change in potential energy. And that's because of this relationship, right? When you lift an object, the work done by gravity is negative, but the potential energy goes up. When you let an object fall, U decreases, the potential energy decreases. Okay. Does that make sense? And do you guys have any questions about that? Got it, memorize. This is just, yep, memorize this. It's going to show up more and more in your physics classes now that you're in the 1 series. Okay. So there's the potential energy due to gravity. Okay. And now, since we already did this for the spring's really easy. Okay. Why won't you let me pick this? Let me change pens. Oh, whoops. There it goes. Okay. Okay. For the spring, we said work done by spring, right, was equal to negative 1/2 But if this has to be equal to the negative of the change in potential energy due to the spring, That is to say it should be equal to the negative of u2 minus u1. Then we can compare both sides of the equations and see that u2 is the energy stored in the spring when it's at point 2, and that's going to be 1/2 k times x2 squared. u1 would be equal to 1/2 k times x1 squared. And in general, right, the energy stored in a spring can be just defined as 1/2 k times how much ever the spring is actually stretched squared. Okay, so there's the potential energy in a spring. Both the spring and gravity are conservative forces, okay, because they have this potential energy function, and the reason why they have a potential energy function is because the work done only depends on the endpoints and not on the path. That's what this all started with, right? We started with saying the work done by gravity is path independent, etc. I really should have zoomed back in before we started again, because now I'm not going to be able to make a nice document of this, but that's okay. Okay? So there we go. 2 different types of energy. We're going to use those to solve maybe 1 problem, maybe 2 problems. We'll see what we have time for. All right? You guys want to do that? You guys okay with these concepts? So the problem we want to solve, we're going to do this one. So we have a block of mass m is at rest, a height h above a spring with a force constant k. We want to find the maximum distance d that the spring is compressed. Kind of want to make this a little bit bigger. Whoops, that's not what I wanted to do. I don't know what I just did. I probably just... There we go. Alright, so there's our problem. Block of mass m is at rest to height h above a spring with a force constant k. Find the maximum distance d that the spring is going to be compressed here. Now, oh, I forgot. Before we do this problem, we got to tie this stuff back together. So let's go back to the work-energy theorem. I forgot. We could solve that problem without doing this, but so our work-energy theorem, right, said that work done was equal to change in kinetic energy, right? But we can break this up into 2 pieces. We can now say this is going to be the work that's done by conservative forces plus the work that's done by non-conservative forces, and that should be equal to the change in kinetic energy of a system. But we just said that the work done by a conservative force is the negative of the change in potential energy, right? So we can change this for negative delta U plus work done by non-conservative forces is equal to delta change in kinetic energy. But then this one becomes, if we add them all together, the work done by non-conservative forces ends up being the change in potential energy, sorry, I'll write it the other way, the change in kinetic energy of an object plus the change in potential energy of an object. And we've learned about 2 different types of this. So this would be the change in potential energy due to a spring, and it can also be the change in potential energy due to gravity. And this general expression right here, okay, is often referred to as conservation of energy. More specifically, conservation of what's called mechanical energy. And mechanical energy is just equal to kinetic energy plus potential energy. Okay, this is one of the most useful equations in all of physics. It tells us that if we calculate the work done by non-conservative forces in a system, it should be equal to the overall change in mechanical energy of the system, the change in the kinetic plus the potential energy of the system. We'll be using this exhaustively in this course. We will use it over and over and over again, and you'll continue to see it used in all of the physics in the 1 series. This is a very, very general equation that it not only applies to classical mechanical systems, but it also applies to really a lot more systems. It applies to a lot of systems, I guess is what I'm going to try to say. Yeah. Conservation of mechanical energy. That's the general equation that we're going to use to solve the problem that we're going to do right here. Okay. So I guess I can leave it on the screen. Just move this up just a little bit. All right, so let's try to solve. This problem here. You have a question, Daniel? Okay. So here's our scenario. We start off with the spring. The spring is uncompressed, right? The block starts off, as it says, a distance here that we call capital H. This is kind of the before. And then after the spring gets compressed some, the block is down here, okay? But now the spring has been compressed by a distance that we're going to call d. And that's ultimately what we want to calculate in terms of the other variables if we know that the spring constant is k. And yeah, we'll probably put some numbers in here to simplify this, but we'll start off by solving it without numbers. Okay. All right. So, what you do in problems like this is you have to label 2 points. So this is our before and this is our after. And we're going to start off by defining all the points that show up in our equation. Let's expand out what this equation looks like now. So this equation is going to state that the work done by non-conservative forces should be equal to change in kinetic energy. Well, we can write that out like this. It's 1/2 mass times second velocity squared, or final velocity squared, minus initial velocity squared, plus the delta U for the spring, we said was 1/2 k times x2 squared minus x1 squared, and then change of potential energy to gravity ends up being mg times y2 minus y1. Okay. We're going to define up as positive, okay, and we need to basically indicate what's going on at each of these points right here, okay? So the first thing we do is to label some things. This block is at rest, so that means that its initial velocity, v1, is going to be 0. Its initial y-coordinate, what's that going to be? Well, it depends on what we define y equal to 0 to be. So for example, if we define this point right here to be y equal to 0, then y1 would be equal to capital H, the height above the spring. And then y2, down here, would be like negative d. v2, also going to be 0. We're looking for the maximum distance the spring is compressed, right? So when the spring is compressed by its maximum distance, the block's not going to be moving. So initial velocity 0, final velocity 0, initial height, final height. The last thing that shows up in this equation is x, so I'm going to say x sub 2 right here. The compression of the spring is going to be d, and for x1 right here, what I'm going to say is the spring is not compressed, so I'm going to say x1 is 0. No compression, x1 is going to be 0. And literally all we have to do is just plug all of these directly into this equation here. I'm going to indicate the things that are 0. So like x1 was 0. V2 is 0. V1 is 0. There are no non-conservative forces acting in this problem. Non-conservative forces are going to be things like friction, drag, stuff like that. So what are we left with here? We just have 0 equals 1/2 k x2 squared plus mg. Now we said that y2 was negative d, right? And minus y1 is h, right? So we end up getting something like that. I made a mistake. Oops. Let's fix this. x2 is not a mistake. I just didn't sub in for x2. x2 is d, right? So we would put in here for x2, we'd put d squared and d squared. Now, in order to solve this problem, we want to solve for d, but we see that d shows up squared. There's the d to the first power, and this would have d to the 0 power, right? So in order to do this, we kind of need some values, right? So let's say that our mass is equal to 2 kilograms. 2 kilograms. Let's say that the height h is equal to 3 meters. And let's say the spring constant k, let's make it equal to 10 or 100, let's let's say newtons per meter. We'll use those values. And we'll also use, let's just use g equal to 10 to keep things simple. So what would we get then? So let's rearrange this a little bit here. I guess I'm going to rearrange it to look like this, aren't I? What does x represent? Like the x here in this equation, Andrew? So x represents the amount that the spring is compressed. It's the amount that the spring is compressed or stretched. It's the, yeah. No problem. So mgd minus mgh, and we just need to plug in some numbers now. So before we do this, does anyone have any questions? Are there other questions? Okay, so m is 2 kilograms, g is 10, and d minus, and then h is 3. So we end up getting 0 equals 100 over this, we 50 d squared, and then 20d, and then 60. These numbers came out kind of nice. We could divide through by 10. There's no way this could be factored, right? Minus 3 is 7. If it was a 1, you could factor it. Anyway, so then we would just plug this into the quadratic, right? And then we can calculate what that's equal to. I'm going to do this on my calculator because I don't like the Windows calculator too much for doing stuff like this. So I got, for the positive root, I got 1.3. And for the negative root, and that's going to be the right answer, 1.3 meters. Okay. Does that make sense? Anyone have any questions? Okay. So that's energy for you. Probably can do one more problem. Could just stop though. I feel like these lectures without me taking time and stopping and saying, hey, solve this, I feel like they're kind of dense. So I might just stop and pick this up next time with the last problem that I wanted to do, because think you guys need to go home and think about things. If you want to, this is what we'll do next time. We'll look at this problem, and we'll talk about power, electrical power. Not electrical power. This is Physics 1A. We're talking about electrical power in my other class. We'll talk about this problem, and then we'll talk about how power works, which is the rate at which energy is done, and do some problems with that too. So there we go. That's work and energy for today. Do you guys have any general questions or comments or anything? Questions about homework? I'm going to go ahead and stop the stream. Or stop the recording.